What if the universe is already far larger than anything we will ever be able to see? Not just larger than our telescopes can reach today, but larger in a way that no future technology could ever overcome. Larger not because of distance alone, but because of how time and space themselves behave. For a long time, it was comforting to imagine that the universe was simply waiting to be revealed. That with better instruments and more patience, the darkness would gradually give way to detail. That the unknown was only temporary, a matter of sharper vision and deeper images. But what if that idea is wrong? What if the universe is not hiding from us, but actively slipping away? Not retreating into darkness, but expanding beyond the limits of what observation can ever recover. When the James Webb Space Telescope began sending back its deepest images, it seemed at first like a breakthrough in reach. Galaxies appeared where there had once been emptiness. Light arrived from eras thought to be beyond view. The early universe did not look quiet or tentative. It looked crowded, luminous, and already complex. Yet beneath that sense of discovery lies a quieter and more unsettling realization. James Webb did not simply show us more of the universe. It revealed how narrow our view has always been. Every image it captures is made of light that has crossed immense spans of time. Each point of brightness is not a place as it is now, but a moment preserved from long ago. The deeper Webb looks, the further back those moments come from, and the closer observation moves toward a boundary that cannot be crossed. There is a limit built into the universe itself, a horizon defined not by technology, but by time, expansion, and the finite speed at which information can travel. To understand why this limit exists, it helps to let go of the idea that space is something we simply look across. In the universe, distance and time are inseparable. Every act of seeing is also an act of remembering. Light does not arrive instantly. It travels carrying with it a record of when it began its journey. Even in everyday life, this delay is present, though it is usually too small to notice. Light from a nearby object reaches the eye a fraction of a moment after it leaves its source. Light from the sun arrives minutes late. These delays feel trivial, but they reveal something fundamental. Vision is never immediate. It is always a glimpse of the past. As observation reaches farther into space, those delays stretch dramatically. The nearest stars beyond the sun are seen as they were years ago. The glowing center of the Milky Way appears tens of thousands of years younger than it is now. When telescopes peer beyond our galaxy, the delay grows into millions and then billions of years. At that scale, the night sky stops behaving like a snapshot. It becomes a layered record of different eras, all visible at once. Nearby galaxies show a universe that feels familiar and mature. Distant ones reveal a cosmos that was smaller, hotter, and far less settled. This effect is intensified by the fact that space itself is not still. The universe expands, and as it does, it stretches the light moving through it. Waves of light lengthen as space grows, shifting energetic radiation toward redder and eventually infrared wavelengths. This stretching is known as redshift, and it turns light into a kind of clock. The more the light has been stretched, the longer it has been traveling, and the earlier the moment from which it comes. Distance alone no longer tells the story. Time and expansion become part of every measurement. For most of human history, this deeper structure of observation remained hidden. Telescopes were designed to collect visible light, the narrow band our eyes evolved to detect. That window works beautifully for nearby stars, glowing nebulae, and familiar galaxies. But as astronomers tried to see farther back in time, the universe quietly slipped out of view. Ancient galaxies did not vanish. The light was stretched beyond what those instruments could register. The darkness was not emptiness. It was limitation. James Webb was built to look where that missing light now resides. Its instruments are tuned to infrared wavelengths, sensitive to radiation that has been stretched for billions of years by an expanding cosmos. To detect such faint signals, Webb operates far from Earth, shielded from heat and cooled to extreme temperatures. In that cold and distant environment, it listens patiently for photons that began their journey when the universe was still young. When Webb observes a region of sky that appears empty to the naked eye, it is not searching for nothing. It is waiting for light that has crossed an immense span of time, slipping through a universe that has been stretching the entire way. Each faint glow it detects marks the end of a journey that began long before planets formed, long before stars like the Sun existed, long before the Milky Way took its present shape. What emerges from these observations is not a gentle or tentative beginning. The early universe appears busy, crowded, and unexpectedly active. Galaxies show up earlier than expected. Structures appear where simplicity was assumed. Space that once looked sparse reveals layers of light stacked behind one another, hinting at depth far greater than intuition allows. The universe does not unfold slowly into complexity. It seems to rush toward it. Yet even as Webb reveals more than any telescope before it, it also brings a deeper truth into focus. There is a boundary that no improvement in technology can cross. A horizon defined not by darkness, but by physics. Beyond a certain point, light has not had enough time to reach us. In some cases, it never will. Space between those regions and here expands too quickly for any signal to close the gap. This means the universe that can be seen is not the universe in its entirety. It is a partial view, shaped by time, expansion, and the finite speed at which information travels. James Webb does not show the edge of existence. It shows how narrow the window of observation has always been. As this realization settles in, the meaning of scale begins to change. The question is no longer how far the universe extends or how many galaxies exist. The question becomes something quieter and far more unsettling. How much of the universe is already beyond reach? At first, the size of the universe feels like something that should be easy to describe. If the cosmos began a little over 13 billion years ago and light travels at a fixed speed, then the most distant things we can see should lie roughly that many light years away. For a long time, this simple picture shaped how scale was imagined. The universe felt vast, but finite. Immense, yet somehow bounded by time and distance working together in a neat and intuitive way. But that intuition quietly breaks down the moment expansion is taken seriously. The universe is not a static stage through which light moves. Space itself stretches. When the light now reaching our telescopes first began its journey, the galaxies that emitted it were far closer than they are today. Over billions of years, the space between its source and its destination continued to grow. By the time the light finally arrived, its point of origin had been carried far beyond where that journey began. Distance was not fixed. It was changing beneath the light the entire time. This is why the observable universe is far larger than its age alone would suggest. The most distant light reaching us today did not travel through a frozen arena. It crossed a universe that kept expanding as it moved. When that expansion is accounted for, the scale becomes startling. The radius of the observable universe is not a little over 13 billion light-years. It is closer to 46.5 billion light-years. The full diameter spans roughly 93 billion light-years, a size that feels almost disconnected from the time since the beginning. This enormous scale is not speculation. It follows directly from how expansion works. Early in cosmic history, matter was denser and expansion was slower. Light made steady progress. Later, expansion accelerated. Distances grew faster. The journey became harder, not because light slowed down, but because the destination kept receding. Eventually, a threshold is reached. Beyond it, light has not had enough time to arrive. In some cases, it never will, no matter how long the universe exists. This threshold is known as the observable horizon. It is not a wall in space. It is a limit on information. Beyond it, galaxies exist, stars ignite, and cosmic history unfolds just as richly as it does here. But no signal from those regions can reach us. The universe does not end at that boundary. Knowledge does. What makes this realization unsettling is that the horizon is not empty. In every direction, space looks remarkably similar. The faint afterglow of the early universe appears nearly uniform across the sky. That uniformity would be impossible if the cosmos abruptly stopped just beyond what we can see. Everything about observation suggests continuity far beyond the limits of visibility. This means the observable universe is not a special region. It is a perspective. From here, this is what can be seen. From another galaxy, the observable universe would be centered there instead. Some regions visible from Earth would lie forever beyond reach from elsewhere, while regions invisible to us would fall within view. There is no single vantage point from which the entire universe can be observed at once. James Webb brings this into sharper focus by showing how close present observations already are to that horizon. When it detects galaxies from the universe's earliest eras, it is capturing light that began its journey when space was far smaller and far denser than it is now. Those galaxies are not just distant. They are separated from us by an expanding gulf that has been growing for billions of years. Their present state, their later evolution, and their eventual fate are already hidden. What is seen is not what exists now. It is what once existed, preserved in light, that managed to arrive before the window closed. This is where the idea of scale quietly shifts again. The universe does not simply grow larger as observation improves. It becomes more incomplete. The deeper telescopes look, the more they reveal how much lies beyond reach. Each new layer of structure uncovered near the horizon implies even more structure that can never be observed at all. And this realization grows even stronger when James Webb turns its attention to the earliest galaxies themselves. When James Webb began revealing galaxies from the universe's earliest eras, the surprise was not simply that they existed, but how many there were and how developed they appeared. The early universe had long been imagined as a quiet place, still finding its footing after the initial heat of creation. In that picture, matter drifted slowly, stars formed reluctantly, and galaxies took a long time to assemble. Complexity was expected to arrive late, after hundreds of millions of years of gradual growth. What Webb showed was something very different. Even when the universe was only a small fraction of its current age, space was already crowded with light. Galaxies appeared in large numbers. Some were compact and intense, others surprisingly extended. Many were forming stars at remarkable rates, converting gas into light with an efficiency rarely seen in the modern cosmos. The early universe did not look like a tentative beginning. It looked busy, energetic, and already organized. This matters because brightness is not superficial. Light comes from stars, and stars require mass, time, and structure to form. Seeing so much light so early means that matter must have gathered quickly, collapsing into dense regions far faster than simple models once assumed. The universe did not wait patiently to become complex. It surged toward complexity almost as soon as conditions allowed it to begin. Even more striking was what the light itself revealed. The glow from these early galaxies carried the signatures of elements heavier than hydrogen and helium. Elements like carbon and oxygen do not appear spontaneously. They are forged inside stars and released only when those stars end their lives. Their presence in such young galaxies means that earlier generations of stars must have already formed, lived, and died, enriching their surroundings in a remarkably short span of cosmic time. The implication is subtle but profound. The universe was not only forming stars early, it was already recycling them. Stellar life cycles were underway while the cosmos was still in its youth. Space was not pristine for long. It was quickly transformed by light, heat, and gravity working together at scale. At the centers of many of these early galaxies, Webb revealed something even more unsettling. Massive black holes were already in place, exerting enormous influence over their surroundings. Some of these black holes possessed masses millions or even billions of times greater than that of the Sun, despite existing when the universe was still very young. According to long-held assumptions, there should not have been enough time for such objects to grow. Under conventional ideas, black holes begin as the collapsed remnants of massive stars. From there, they grow gradually by pulling in nearby matter. But this process is limited. As material falls inward, it heats up and releases energy, pushing back against further growth. Even under ideal conditions, building extremely massive black holes takes a long time. And yet, Webb continues to find them in the early universe. This has forced astronomers to consider more extreme possibilities. Perhaps some black holes formed directly from the collapse of enormous gas clouds, skipping the stellar phase entirely. Perhaps the first stars were far more massive than those seen today, collapsing almost immediately into large black holes. Perhaps mergers were far more frequent in the dense early universe, rapidly combining smaller black holes into larger ones. Each idea stretches understanding, but none can be dismissed. What matters most is not which explanation proves correct, but what these early black holes reveal about the universe itself. They show that gravity worked quickly and efficiently. That matter did not drift aimlessly for long. That structure assembled at a pace that leaves little room for simplicity. Together, the early galaxies and their black holes point to a universe that filled itself in rapidly. Space that once seemed empty reveals itself as densely populated almost from the beginning. Light appears not as isolated points scattered through darkness, but as a continuous presence layered across time. And this density carries a powerful implication for scale. If so much structure exists near the limits of observation, then the portion of the universe we can see is likely only a small sample of what exists overall. Every galaxy detected near the horizon suggests many more just beyond it, forming and evolving without ever sending light that can reach here. This becomes even clearer when astronomers attempt to answer a deceptively simple question. How many galaxies are there? For decades, the answer was thought to be on the order of hundreds of billions. That estimate came from deep observations of small patches of sky, where telescopes counted every visible galaxy and then scaled that number up to represent the entire observable universe. The results were staggering, yet they felt complete. The darkness between galaxies appeared real. The gaps seemed genuine. James Webb changed that impression almost immediately. When Webb observed similar regions of sky, the darkness softened. Faint glows appeared where emptiness was expected. Smudges resolved into distinct systems. What once looked like gaps filled with structure. The universe did not simply contain more galaxies than expected. It appeared woven together more tightly than imagined. In some of Webb's deepest views, regions of sky no larger than a grain of sand held at arm's length contain tens of thousands of galaxies. Each one is an entire system, containing millions or billions of stars. Many host planets. Many contain the chemical ingredients for complexity. The universe revealed by Webb is not sparse. It is densely populated at every scale observation can reach. As these counts accumulate, estimates shift again. The observable universe may not contain mere hundreds of billions of galaxies, but trillions. For every galaxy once counted, several more may have gone unseen until now. And even this revised number almost certainly underestimates what exists, because the faintest and most distant systems remain beyond detection. This abundance does not appear random. Galaxies trace vast filaments stretching across space, intersecting at dense nodes and avoiding enormous regions almost entirely. On the largest scales, matter forms a cosmic web, a structure shaped by gravity, acting over billions of years. James Webb's infrared vision has begun filling in missing sections of this web, revealing how early and how completely it took shape. Yet alongside this richness lies immense emptiness. Between filaments lie vast voids, regions spanning tens or hundreds of millions of light years that contain very few galaxies. These voids are not small gaps. They dominate the volume of the universe. If one could exist within their centers, darkness would extend in every direction for unimaginable distances before the nearest galaxy appeared. This contrast between crowded filaments and empty voids reveals something essential about cosmic scale. The universe was never evenly filled. From its earliest moments, gravity sculpted matter into regions of abundance and regions of absence. What appears as emptiness is not failure. It is structure expressed on the largest scales. And all of this, the galaxies, the filaments, the voids, exists only within the portion of the universe that happens to be observable now. Beyond that boundary, space continues. Structure continues. Galaxies form, collide, and evolve without ever becoming visible from here. The deeper James Webb looks, the more clearly this truth emerges. The universe is not only vast, most of it is permanently out of reach. As the picture of abundance sharpens, another force quietly steps into view, one that does not build structure, but steadily stretches it apart. The universe is expanding, and it is not doing so gently or uniformly. Over time, the rate of expansion has changed, reshaping not only distances, but the fate of what can ever be observed. For much of the 20th century, expansion was assumed to be slowing down. The universe began in a hot, dense state. Matter rushed outward, and gravity worked over billions of years to pull that motion back. Whether the cosmos would expand forever or eventually collapse inward was an open question, but gravity was expected to dominate the long-term outcome. Expansion felt like a fading echo of the beginning. Careful observation overturned that expectation. By studying distant stellar explosions with predictable brightness, astronomers discovered that faraway galaxies were not merely receding, but accelerating away from one another. Space itself was expanding faster now than it had in the past. Something was pushing against gravity on the largest scales, overwhelming its ability to slow the universe down. To account for this behavior, cosmology introduced a new component, one that does not emit light, absorb radiation, or form structures of its own. This component became known as dark energy. Dark energy is inferred entirely from its effects. It reveals itself through motion rather than appearance. Measurements show that it makes up most of the universe's total energy content, far outweighing ordinary matter and even dark matter combined. What makes it especially strange is how it behaves as the universe grows. As space expands, matter becomes more spread out. Its influence weakens. Dark energy does not dilute in the same way. Its density remains nearly constant even as space stretches. This creates a feedback effect that reshapes cosmic history. As the universe expands, the total amount of dark energy increases. That added dark energy drives even faster expansion, which creates more space, which in turn produces more dark energy. Over billions of years, this quiet process comes to dominate everything else. Early in the universe's life, matter was dense enough for gravity to sculpt structure. Galaxies assembled, stars ignited, and the cosmic web took shape. But as expansion continued and matter thinned, dark energy gradually overtook gravity on the largest scales. Several billion years ago, this transition became decisive. Expansion stopped slowing down and began to accelerate. James Webb does not observe dark energy directly, but its influence is written into every deep image. The extreme stretching of ancient light, the enormous size of the observable universe, and the growing separation between distant galaxies all reflect its presence. Webb's discoveries make sense only in a universe where expansion is not merely ongoing, but accelerating. This acceleration has a profound consequence that reshapes the meaning of scale. The observable universe is not a fixed region. It changes with time. Light from distant regions continues to arrive, slowly expanding the boundary of what can be seen. But at the same time, expansion is pushing many galaxies away faster than light can ever cross the growing gaps. The result is a universe where visibility is temporary. Galaxies that are observable today will not remain so forever. As space stretches, their light shifts to longer wavelengths, fading gradually from detectability. Eventually, new photons from those galaxies will never reach Earth. Their images will freeze at a particular moment in cosmic history, then slowly dim as expansion carries them beyond reach. From this perspective, the cosmic horizon is not only a boundary of the past, it is a boundary of the future. Regions of space that now belong to the observable universe will one day slip beyond it, not because they cease to exist, but because the universe expands in a way that prevents information from ever arriving. If the behavior of dark energy remains unchanged, the far future becomes stark. Over tens of billions of years, galaxies beyond the local gravitationally bound region will disappear from view. What remains observable will be a small island of stars surrounded by darkness, with no visible trace of the vast cosmos that once filled the sky. Future observers in that distant era would see a very different universe. The night sky would contain only nearby galaxies, bound together by gravity. Beyond them, space would appear empty and still. There would be no obvious evidence of expansion, no visible cosmic web, no distant clusters of galaxies receding into the dark. Those observers might never suspect that the universe was once filled with trillions of galaxies spread across immense distances. The evidence would be gone, stretched away by expansion. The universe would appear smaller, quieter, and more isolated, not because it is, but because visibility has narrowed. This realization adds a new dimension to scale. The universe is not only large, it is changing in how much of it can be known. Scale becomes time-dependent. What can be observed depends not just on where you are, but when you are. James Webb sharpens this awareness by showing how close present observations already are to the horizon of visibility. Many of the galaxies it detects exist at distances where their future light will never reach Earth. What is seen is not a continuing story, but a preserved moment, a snapshot of a universe that is already slipping away. This makes the abundance revealed by Webb feel both astonishing and fragile. Trillions of galaxies may exist within the observable universe now, yet most of them are destined to vanish from view over cosmic time. The universe is not simply expanding into emptiness. It is expanding in a way that erases its own history from observation. At the same time that dark energy stretches the universe apart, another unseen component works quietly in the opposite direction. One that does not accelerate expansion, but instead binds matter together and gives structure to the cosmos. This component is dark matter. Dark matter does not shine. It does not emit or absorb light. It does not interact with radiation in any way that telescopes can detect directly. Its presence is revealed through gravity alone. And without it, the universe revealed by James Webb could not exist in its present form. The first clues to dark matter appeared long before Webb. Astronomers studying spiral galaxies noticed that stars in their outer regions orbit far faster than visible matter alone could explain. According to the mass that could be seen, those stars should have flown apart into intergalactic space. Instead, they remained bound, moving as if surrounded by vast halos of invisible material. The same pattern appeared on larger scales. Galaxies within clusters moved too quickly to be held together by visible matter alone. Light from background objects bent more than expected as it passed through these regions, revealing gravitational influence without corresponding light. Again and again, observations pointed to the same conclusion. Most of the universe's matter is invisible. Roughly 85% of all matter consists of dark matter. Ordinary matter, everything from galaxies to planets to living beings, makes up only a small fraction of what exists. What gives dark matter its importance is not just how much of it there is, but how it behaves. Unlike ordinary matter, dark matter does not collide with itself or lose energy through radiation. It moves through space, almost frictionlessly. This allows it to begin clumping very early in cosmic history, long before stars or galaxies could form. Shortly after the universe began, tiny variations in density existed throughout space. Dark matter responded first. While ordinary matter remained hot and resistant to collapse, dark matter gathered into invisible concentrations known as halos. These halos grew steadily under gravity, forming the underlying framework of the universe. As the universe cooled, ordinary matter fell into these dark matter wells. Gas collected, compressed, and eventually ignited stars. Galaxies did not form randomly. They formed where dark matter had already assembled, tracing an invisible structure laid down billions of years earlier. This process produced the cosmic web. Vast filaments of matter stretching across space, intersecting at dense nodes where galaxy clusters formed, separated by enormous voids. What appears as a pattern of galaxies in deep images reflects a deeper structure defined by dark matter alone. James Webb's infrared vision has begun to reveal this structure with greater clarity. By detecting faint and distant galaxies that earlier surveys missed, Webb fills in missing segments of the cosmic web. Filaments that once appeared incomplete now emerge as continuous, revealing how early and how thoroughly matter organized itself on the largest scales. These filaments are not static. Matter flows along them. Gas streams toward dense regions, feeding galaxies and clusters over billions of years. Even the Milky Way resides on one of these filaments, connected by invisible pathways to larger structures drifting through space. At the intersections of filaments lie galaxy clusters, the most massive gravitationally bound structures in existence. A single cluster can contain hundreds or thousands of galaxies, vast reservoirs of hot gas, and enormous quantities of dark matter. These clusters act as anchors, pulling matter inward and shaping the evolution of everything around them. When galaxies fall into these dense environments, they change. Gas is stripped away. Star formation slows or stops. Shapes become smoother and more uniform. Webb has observed these transformations in detail, capturing galaxies in the process of being reshaped by their surroundings. Yet for all its influence, dark matter remains deeply mysterious. Its composition is unknown. It may consist of particles beyond current physics or involve phenomena not yet imagined. Decades of experiments have searched for direct detection without success. And still, its gravitational signature is undeniable. Remove dark matter from the picture, and the universe falls apart. Galaxies could not form. Clusters would not exist. The cosmic web would dissolve into a nearly uniform fog of matter. James Webb does not solve the mystery of dark matter, but it reinforces its central role. By revealing how quickly structure formed in the early universe, Webb shows that an invisible gravitational framework must have been present from the very beginning. Together, dark energy and dark matter define the universe's large-scale behavior. One stretches space apart. The other binds matter together. The cosmos exists in a constant tension between these two unseen forces. And within that tension lies the true sense of scale that James Webb has revealed. Seen together, these forces reshape what scale really means. Dark matter builds structure quickly and efficiently, allowing galaxies to form early and in great numbers. Dark energy stretches space relentlessly, separating those structures and limiting how much of them can ever be seen. The universe becomes both richly populated and increasingly inaccessible at the same time. Abundance and loss advance together. This tension explains why James Webb's images feel so unsettling. They do not simply show distant objects. They show a universe that became full very early, then began to pull itself apart. Structure appears almost everywhere Webb looks, even near the limits of observation. There is no sense of thinning out, no suggestion that the universe grows sparse with distance. Instead, the cosmos appears crowded right up to the edge of what can be seen. That edge is not quiet. When Webb observes the deepest regions of space, it does not encounter emptiness. It encounters overlap, galaxies layered behind galaxies, light stacked upon light, entire histories compressed into a single field of view. Each faint point represents an entire system, already mature, already shaped by gravity, already participating in the cosmic web. The universe does not fade gently into darkness. It remains busy until observation simply stops. This is where scale becomes difficult to hold intuitively. The observable universe already spans roughly 93 billion light-years from one side to the other. It contains trillions of galaxies, vast filaments of matter, and enormous voids carved between them. And yet, everything within that immense volume represents only what light has managed to deliver to this location so far. Beyond it, the universe continues without interruption. There is no indication that physics changes abruptly at the horizon. The same laws that govern stars, galaxies, and black holes here appear to operate everywhere. Observation is possible. The uniformity of the early universe, the consistency of cosmic structure, and the repeating patterns revealed by deep surveys all point toward continuity far beyond what can be seen. Which means the observable universe is not a container holding everything that exists. It is a sample, a time-limited, location-dependent slice of a much larger whole. Every deep image assembled by James Webb is shaped by this constraint. The telescope does not show the universe as it is now. It shows the universe as it was, across a wide range of moments stitched together by light. Nearby objects appear relatively recent. Distant ones appear ancient. What looks like a single scene is actually a collage of different eras layered into the same sky. This layering introduces a quiet asymmetry. The past remains visible. The future does not. Light arrives carrying history, but no return signal is possible. Galaxies whose ancient light reaches us today may already be unrecognizable now, altered by mergers, star formation, and internal change. That information is already lost to expansion. Observation becomes an act of reconstruction rather than inspection. And this is where James Webb's role becomes clearer. It is not simply extending vision farther outward. It is compressing time, bringing together epochs that would otherwise remain separated by billions of years. It allows the universe's early density to be seen directly, revealing how quickly space filled itself with structure. That density is the key. If galaxies were already abundant and organized when the universe was young, then the total amount of structure that exists today must be staggering. Billions of years of continued evolution, mergers, and star formation have followed since those early moments. The portion of the universe that lies beyond the observable horizon has had just as much time to develop, which means the universe beyond reach is not likely to be simple, empty, or sparse. It is likely rich, structured, and crowded in much the same way as the portion we can see. This realization strips away the comfort of imagining the unknown as distant emptiness. The darkness beyond the horizon is not a void waiting to be filled. It is a region filled already, simply inaccessible. What separates us from it is not distance alone, but the behavior of space itself. From this perspective, the observable universe begins to feel less like a map and more like a memory. A record of what managed to send light before expansion carried everything too far apart. Each galaxy visible near the horizon represents not only presence, but loss. A final message delivered before the connection closed. And that loss is not confined to the distant past. It is ongoing. As expansion accelerates, the observable universe does not grow richer. It grows thinner. New light from nearby regions continues to arrive, but distant galaxies slowly fade from view. Over time, the balance shifts. More disappears than appears. Visibility contracts even as space itself grows larger. This leads to a deeply counterintuitive outcome. The universe becomes physically larger while observationally smaller. More exists, yet less can be known. James Webb sits at a rare moment in this process. Early enough that vast regions of the universe are still visible. Late enough that expansion has already erased many connections. The images it captures belong to a narrow window in cosmic history, a period when the universe is both richly populated and still partially accessible. This window will not remain open forever. Billions of years from now, the deep sky will look profoundly different. The most distant galaxies Webb observes today will have slipped beyond reach. The cosmic web will no longer be visible in its full extent. Expansion will have stretched space so thoroughly that only a small region of nearby galaxies remains observable. From within that future, the universe would appear simpler and quieter than it truly is. The evidence of vast scale would be gone. The richness revealed by Webb would lie entirely in the past, inaccessible to observation. This gives James Webb's discoveries a subtle urgency, not in a human sense, but in a cosmic one. The universe allows itself to be seen only briefly on its own terms. What can be observed depends on timing as much as technology. And this brings the idea of scale to its final and most unsettling form. Scale is not just about how big the universe is. It is about how much of it can ever be seen. Seen this way, The James Webb Space Telescope becomes something more than an instrument of discovery. It becomes a witness to a fleeting alignment between existence and observability. A moment when the universe has grown vast and complex, yet has not fully erased its own distant past from view. Every deep field image Webb produces carries this tension within it. The galaxies appear serene and stable, frozen points of light against a dark background. But that calm is misleading. Each of those galaxies is moving away. Each is being carried outward by the expansion of space itself. The light reaching us now left its source long ago, at a time when the universe was smaller and more tightly connected than it is today. What Webb captures, then, is not a present reality, but a preserved one. A universe caught mid-transition, still visible across enormous distances, but already in the process of becoming observationally fragmented. This fragmentation does not happen suddenly. It unfolds gradually, almost invisibly, over billions of years. Light continues to arrive from distant regions, but it arrives more stretched, more weakened, more diluted by expansion. Eventually, the stretching becomes too extreme. Wavelengths grow so long that no detector can register them. Signals fade, not because their sources vanish, but because space itself pulls them beyond reach. In this sense, expansion acts like a slow eraser, not removing objects from existence, but removing access to them. The universe does not grow empty. It grows silent. James Webb reveals just how advanced this process already is. Many of the galaxies it observes lie so far away that their future light will never reach Earth. What we see from them now is all that will ever be seen. Their ongoing histories, their future mergers, their eventual transformations are already sealed off by expansion. This realization quietly alters the meaning of discovery. Observation is no longer about uncovering what exists. It becomes about recovering what can still be reached before it is lost. The universe begins to resemble a vast landscape seen through closing doors. Each door shuts, not because of distance alone, but because time and expansion conspire to limit connection. What remains visible is not chosen by importance or size, but by timing. This makes the present era cosmologically unusual, not privileged in any special sense, but rare. The universe has reached a stage where structure is fully developed, galaxies are abundant, and light from the early cosmos is still arriving. That combination will not last indefinitely. Earlier in cosmic history, the universe was too young. Structure had not yet formed. Later, it will be too expanded. Structure will still exist, but much of it will no longer be observable. The present sits between those extremes, offering a partial but remarkably rich view. James Webb operates precisely within that window. Its images show a universe that wasted no time becoming complex. Galaxies formed early, black holes grew rapidly, and matter organized itself into vast networks almost as soon as conditions allowed. This efficiency suggests that the universe beyond the observable horizon has had just as much opportunity to develop richness and structure. There is no reason to believe that complexity stops where observation stops. If anything, Webb's discoveries argue the opposite. If space near the horizon is already crowded, then regions beyond it are unlikely to be empty. They are simply unreachable. This removes a subtle but persistent illusion: the idea that darkness implies absence. In the cosmos, darkness often means distance, time, or limitation. The blackness beyond the deepest images is not a void waiting to be filled by better instruments. It is a region filled already, simply beyond the reach of light. Seen from this perspective, the observable universe becomes a shrinking island within a much larger ocean of existence. not shrinking in physical size, but in informational reach. What can be known contracts even as what exists continues to grow. And this contraction is not symmetrical. Nearby structures remain accessible. Distant ones are lost first. Over time, observation collapses inward. The far universe fades. The near universe dominates. Eventually, only the local group of galaxies remains visible, bound together by gravity and isolated within an expanding void. From within that future, the universe would appear deceptively simple. A small collection of galaxies surrounded by darkness. No visible evidence of vast cosmic structure. No hint of trillions of galaxies beyond reach. No obvious sign of expansion. Those future observers might construct a very different picture of reality, one shaped not by what exists, but by what remains observable. Without access to the deep sky, the true scale of the universe would be hidden, not by ignorance, but by physics. James Webb allows us to glimpse that true scale precisely because we live before that loss is complete. It shows a universe that is both immense and transient in its visibility. A cosmos filled with structure that will one day slip quietly beyond reach, leaving behind only local remnants and fading memories encoded in ancient light. This is why Webb's images feel simultaneously triumphant and melancholic. They expand understanding, but they also reveal limits. They show abundance, but they also show fragility. Not fragility of existence, but fragility of access. The universe does not promise to remain visible. It reveals itself briefly, then moves on. And it is within this narrow interval, this brief overlap between existence and observability, that the true scale of the universe becomes apparent. Seen from this wider perspective, the James Webb Space Telescope becomes something more than an instrument built to collect distant light. It becomes a lens through which the structure of limitation itself comes into focus. It shows that the universe is not arranged to be fully revealed from any single place at any single moment in time. Observation is not a right granted by technology. It is a condition shaped by physics, expansion, and the finite speed at which information can travel through space. For centuries, it was natural to imagine that the universe was simply waiting to be uncovered. That darkness marked the edge of current knowledge, not the edge of what could ever be known. Each new telescope seemed to confirm that belief, pushing deeper, resolving finer detail, filling in what once appeared empty. Progress felt directional. The unknown always seemed temporary. James Webb disrupts that assumption quietly but decisively. The images it returns are not just deeper versions of what came before. They show a universe already rich and structured right up to the boundary of visibility. Galaxies do not thin out gently with distance. They remain numerous, layered, and complex until observation simply stops. There is no gradual fading into emptiness. There is only a limit beyond which light has not arrived, and in many cases, never will. This reframes what scale actually means. The true scale of the universe is not defined by the most distant galaxy ever detected, or by the largest number that can be attached to cosmic size. It is defined by the growing gap between what exists and what can ever be observed. James Webb does not close that gap. It illuminates it. Within the observable universe alone, the richness is staggering. Trillions of galaxies may exist, each containing billions of stars. Many of those stars host planetary systems. Many planets orbit within environments where chemistry becomes complex and long histories unfold. Vast filaments of matter stretch across immense distances, connecting galaxies into a cosmic web, while equally vast voids open between them. regions so large that light can travel for hundreds of millions of years without encountering a single galaxy. And yet, all of this abundance exists only within the narrow region that happens to be observable now. Beyond that horizon, space does not end. There is no sign of an abrupt boundary where reality gives way to nothing. Everywhere observation is possible, the same physical laws appear to operate. Matter behaves consistently. Structure repeats. Patterns scale. The most reasonable conclusion is that the universe beyond reach is not fundamentally different from the universe we see. It is simply inaccessible. James Webb makes this unavoidable by showing how much already exists near the limits of visibility. If the universe is crowded and organized right up to that boundary, then the regions beyond it have likely had just as much time to develop complexity. Stars would have ignited. Galaxies would have assembled. Black holes would have grown. Entire cosmic histories would have unfolded without ever sending a signal that could arrive here. This realization quietly changes the meaning of discovery. The goal is no longer to search for an edge, because no such edge exists in space. Instead, discovery becomes an effort to understand constraints. To understand not just what exists, but why so much of it lies forever beyond reach. Every deep field image becomes a reminder that observation is selective. Every distant galaxy represents both presence and loss. A message that arrived just in time, before expansion stretched space too far for any further information to cross. The universe offers glimpses, not completeness. From this perspective, the observable universe begins to feel less like a complete map of existence and more like a temporary cross-section of a far larger whole. A slice taken at a particular moment in cosmic history, shaped by expansion, preserved by light, and bounded by physics rather than technology. James Webb arrived during a brief and unusual chapter in cosmic history, not because humanity is special, but because timing matters in an expanding universe. We exist at a moment when structure is fully developed, galaxies are abundant, and light from the early universe is still arriving. That overlap will not last forever. Earlier in cosmic time, the universe was too young. Stars had not yet formed in large numbers. Galaxies were still assembling. The sky would have offered little sense of scale or structure. Later, the universe will be too expanded. Galaxies will still exist, but most will no longer be observable. Expansion will stretch space so thoroughly that only nearby systems remain visible, bound together by gravity and isolated within an ever-growing darkness. James Webb operates between those extremes. Its images capture a universe balanced between accessibility and loss. A cosmos that has already filled itself with structure, yet has not fully erased its own distant past from view. This balance gives the telescope's discoveries a quiet urgency, not in any human sense, but in a cosmic one. The universe allows itself to be seen only briefly, on its own terms. As expansion continues, the observable universe will not grow richer. It will grow thinner. Distant galaxies will fade as their light stretches beyond detectability. Connections will be lost, not because anything disappears, but because space itself changes how information moves. What remains visible will collapse inward toward the local, while the vast majority of existence slips permanently beyond reach. From within that far future, the universe would appear deceptively simple. A small group of nearby galaxies surrounded by stillness and dark. No visible cosmic web. No distant clusters. No obvious evidence that the universe was once crowded with light across immense distances. The true scale of reality would be hidden, not by ignorance, but by physics. Those future observers might never know how large the universe truly is. James Webb allows us to see it precisely because we live before that narrowing is complete. It shows a universe that is not only vast, but fleeting in its visibility. A cosmos whose true scale is revealed not by how far it stretches, but by how much of it can never be fully known. What lies beyond the horizon is not empty. It is simply unreachable. This understanding changes the emotional weight of every deep image. Each distant galaxy is not just an object. It is a moment rescued from loss, a final signal delivered before expansion closed the path behind it. The universe does not reveal itself all at once. It offers fragments, layered across time, bound by limits that no technology can remove. The James Webb Space Telescope does not show the edge of existence. It shows the shape of our limits within it. And in doing so, it reveals the true scale of the universe, not as a number to be memorized, but as a quiet and enduring reminder that reality is far larger than anything that can ever be fully seen.